Hey everybody, it's Mr. Sheeline here as we load into our notes. So this is going to be going over the notes, the Unit 2.1 note solving equations in science, in case you were not in class for this particular lecture. So, all right, let's just get right into it. So, all right, before I get into it, arguably you should have these ones printed off. I will have the student copy of this available for you to print off in the case you're at home, so you can follow along and fill in some notes. So the learning objectives, there's only two in here. They're pretty simple. I can read algebraic equations and apply the same math rules to problems in the science class. I can identify, analyze, and organize data into the appropriate variables. Okay, so the first one here, the first one listed, arguably this one, not so important to focus on because you should be coming to this class already meeting the standard. This is the one that hopefully by the end of this week, you'll be able to at least be better at, maybe not so much completely fulfill, but be better at and to have some practice behind so that we're not completely new, completely green, completely caught unaware by the time that we get to motion and also energy. Okay. So let's get going. So this is something that you've already should have been practicing with. So on Friday, you should have been practicing with equations. So what is an equation? An equation is a mathematical, not just Friday, but also Thursday as well, in case whether you're an A or B day student. An equation is a mathematical sentence with an equal sign. An example of that looks like these. Again, things you've already seen before. Okay. 9 plus 2 equals 11. X plus 7 equals 37. A plus negative 3 equals 2A plus 5. Okay? So again, these are things that we have already been working with, that you have already been studying with, that should not be, terribly new. So where do we see these kinds of equations? Well, we see them everywhere, between science classes to math classes, of course, but also history classes. We also should see them in maybe even English classes as well. Though it'll be under a somewhat different context, they will still nonetheless be in those classes. Now, what about the real world? Well, in the real world, we do see them in carpentry, we see them in plumbing, we see them in automotive, we see it in nursing, we see it in teaching, we see it in accounting. I mean, just on and on and on and on. Even farming. I mean, farming, you use algebra like this. It's found everywhere. Now, I'm not going to lie to you and say, you use math all the time and blah, blah, blah all the time. Sure. Okay. Whatever. Yes. Math is incredibly important. Do you use math every waking second of every waking breath that you have? And is it something that you consciously use at all times? No. I get that. But the point being, you do use it and we do use it in the real world. We do use it in more places than you think. It's also a lot simpler than you think, okay? Which is what we're going to be practicing and seeing, especially when it's applied in science. So what's the solution? A solution within an equation is a value for a variable that makes an equation true. So as an example of that, it's to say that, well, if your equation 170 plus x is equal to 200, well, after solving, your solution should be that, x equals 30. Okay? Well, let's see if that makes that true. So if x indeed is equal to 30, if we add 170 to 30, does that give us 200? If you can do that in your head, then yes, of course, we do get 200. If you have got to put it on the calculator, plot it on the calculator and just double check. And when you do, you'll find out that yes, 170 plus 30 does equal 200. Okay. No different than here. 3 is equal to 12 minus a, where a is equal to 9. Okay. Well, plot it in. 3 is equal to 12 minus 9. Well, what is 12 minus 9? 12 minus 9 is 3. Okay, so 3 is equal to 3. It does make it true. Now, operations. we have to remember and understand this word. An operation is the calculation using different operands. Well, what are operands? Operands are just these guys listed down here. Okay, operands are just these. The adding, subtracting, and the multiplying, dividing, and the equals. All of this right here, those are your operands. Okay, operands is a fancy word that just means what type of what type of operation. Operands are the types of operations. So adding is an operand, subtracting is an operand, multiplying, dividing, they're both operands. Okay, just think of it as what symbols are you using? What do the symbols mean? If you've got a plus sign, if it's X, if it's like this up here, right? Come on, pencil. So up here, what's the operation? Operation is 170 plus X. What's your operation here? It's 12 minus A. Okay. So that's your operation. And I use this language a lot in class. I'll ask you if I'm looking at the work that you're doing. If I see the work that you're doing or if I just ask you about the work that you're doing, I'll ask, what operation do you use? Or are you sure that was the operation you should have used? That's what I'm asking here is what particular operand did you use? What particular kind of math are you using here? And we have to understand operation because then we have to understand what an inverse operation is. And the inverse operation is an operation that undoes another operation. It's the opposite. So, and as an example, add to subtract, multiply to divide. So let's check this. Come on. So on the next slide here, let's check your understanding. So draw a line connecting the inverse operations below. Well, we see we've got addition, multiplication, division, subtraction. What we should see is that addition, it should be connected to subtraction. And then multiplication should be connected to division. Okay. These two are connected. These two are opposites, whereas these two are opposites. Okay. You don't, if you have 9 plus x is equal to 10, you don't for whatever reason multiply by 9 to both sides. Okay, you don't do this. That's not what you do because addition is not or multiplication is not the opposite of addition. Okay, that's just not how it works. So make sure that we understand that and use the proper inverse operations. Okay, so when we are solving for one-step equations, our rule number 1, when you solve an equation, your goal is to get the variable alone by itself on one side of the equation. In other words, if you're trying to isolate, or in other words, you are trying to isolate the variable. Okay, rule number 2. When you are solving for the variable, you must use inverse operations to isolate the variable on one side of the equation. Okay, pretty much what we've already been talking about. Then finally, number 3, whatever you do to one side, you must do to the other. Okay, if it is not equal, if your equation is not equal or balanced, if you did not do this to both sides, it will be wrong. Okay. Now, for the most part, by this point, we should know, we should remember that, yeah, of course, we do it to both sides. But I will be asking you guys as we practice these, if you've got to add 9 to both sides, okay, if you've got to add 9 to both sides, if you just say you've got to add 9 to one side, I'll clarify and say, are you sure about that? I'll clarify and ask, are you sure it's only the one side you have to do that to? Okay. And that may seem redundant and that may seem a little silly, but no, it's an important concept to remember. What you do from one side of an equation, you have to do to the other. Think of it like solving or like lifting weights. So if you add or subtract weight from one side of the barbell, you must add or subtract the same amount of weight to the other side, from the other side of the barbell to keep it balanced. And that's true whether you're about to bench some weight, or if you're taking the weight off. You don't want to take weight. You don't want to take all the weight off of one side of a barbell and then the other side, because that's dangerous. The same thing that you don't load up one side of your barbell with 90% of the weight and 10% on the other side. That's dangerous. Also, it's kind of silly. Okay. Same thing with equations like this. So here's just more or less just laying it out further. When you're solving an equation, you must use the inverse operation to isolate the variable on one side of the equation. Remember, if you add or subtract a number from one side of the equation, you must add or subtract the same number from the other side of the equation. So let's do this step by step here. Okay. So pause the video here, solve these yourselves, and then come back to them just to double check, because you should get these, but then come back to double check to make sure you get the correct answer. So pause it here, and then we'll continue. Okay, so let's solve these. So for the most part, these are pretty super simple. So x plus 4 is equal to 6. What do we do here? Well, what do we do? Well, we want to get this x all by itself. So because we have a plus 4 here, we know that what we need to do then is we need to do this. We know then we've got to do the opposite of this guy. So if it's plus 4 over here, we need to subtract 4 to both sides. Okay, this cancels out, that cancels out, and we should be left with this. We should be left with x is equal to 6 minus 4, and then we just solve. X is equal to 2, and we have our answer. Okay. Same thing down here. So 12 is equal to y minus 5. Now, arguably, these two you could do in your head, but what do we do here? Well, we can see that, oh, well, we need to solve for y, so we need to get y by itself. So to get y by itself, we need to add the 5 to both sides. So it'll be 12 is equal to y minus 5. So there'll be plus 5. Do it to both sides. So then we're left with, and then that cancels out, that cancels out. And then we should be left with y equaling 5 plus 12. And 5 plus 12 is going to equal 17. And then we have our answer. Okay. Pretty simple, right? We've done this before. We've seen this before. We've been here before. Name that movie. Okay. It's Lord of the Rings, by the way. But anyway. Oh, shoot. So then we've got multiplying, dividing. These are literally the same it's the same, what's it called? These are the same bolded words. The only difference is this under the remember. Excuse me. Under the remember, instead of addition and subtraction, it's multiply and divide. Okay. So solving one-step equations. Solve each equation for the variable. So we have 2p is equal to 18, x divided by 14 is 2. So pause the video here, solve these yourselves, and then hit play again to double check to make sure that you solved correctly. Okay, so 2p is equal to 18. So the same thing applies here that we did for addition, Mr. Penn. So 2p is equal to 18, and we want that p all by itself. That's all we want is the p. So to get p by itself, we have to do the inverse of whatever that 2 is doing. So because that 2 is multiplying against the p, we should know that we need to divide. So it should be 2p divided by 2. And what we do to one side, we have to do to the other. So this cancels out, and we should be left with p is equal to 18 divided by 2. And we should then understand or put into our calculator to solve for it and see that 18 divided by 2 is 9. Okay. This guy right here, x over 14 is equal to 2. Same thing, only different. X is over 14. We want to get the X by itself. So it'll be 14 multiplied on both sides. That cancels out and that cancels out. You should be left with X is equal to 2 times 14, which is X is equal to 28. Okay. Easy peasy, right? And it is. And it must seem kind of weird that I'm kind of going through this and saying, well, yeah, this is algebra. You've done this before. You've practiced this before. Why are we practicing it right now in this class? I'll tell you, because when we get to the problems, the examples where it's more science-related material in it, it's not so easy. It's the same principles, same rules, maybe not as easy. Okay. So when we are working in science with math problems, most of the time they're word problems. Most of the time they are a bit more challenging in that respect. Most of the time they rely upon you understanding the context of the scenario. So what do? Well, first you must identify the variables using context clues within a word problem. Okay, we have to identify the variables. Next, you need to be able to identify which variable is the unknown. You need to know what you're solving for. What is it that you're missing? Okay, and we label that very clearly. Third, list the different variable symbols. And where you list those, you list them right below your word problem. Okay, fourth, link the variables listed, link the values listed with the variable symbols. Fifth, write out or identify the equations you need to use. And then the sixth step really would be solve. Okay. So how do we write the variables how do we write the variables? I should not say in, it should say how do we write the variables from a word problem? And simply put, just write them directly beneath the word problem. Okay. And really it should be in the order that you read them. Okay. And we'll get a sense of that when we get to the next check your understanding. So what you're doing here, more or less, what this can be broken down to is you're just identifying what you know and what you don't know. And just so you're aware, similar to operations, this is the kind of language I use here. I'll be asking you guys a lot. Well, did you write down what you know and what you don't know? Okay. Well, what do you know? What don't you know? What are you solving for? What do you have and what do you not have? That's what you're showing. So let's maybe kind of go through and see what that looks like. And I'll have to kind of finagle this a little bit just so I have, what would be the word? I've got more room to write. Okay. Let's see. Okay. So Jenny was hungry. So she went to eat her stash of Halloween candy. She first started with a number of candy bars and then ate 6. She is now left with 94 candy bars. How many candy bars did she start with? So pause it here. Try to solve this for yourself. And then we'll come back and answer this. Okay. Okay, so what do we do here? Jenny was hungry. She wanted to eat some candy. We know she ate 6. Now she's left with 94. Okay, what do we do? Well, for the most part, most of us probably looked at this and kind of laughed and said like, oh, well, I can just do this in my head. Why do I need to write this down? Fair enough. You don't really need to write this down because it's so simple. And what you should have figured out is that, yeah, she used to have 100. Now she has 94 because she ate 6. That makes sense. But if we wanted to write this down, okay, if we want to identify the variables, we would write it like this. So Jenny first started with a number of candy bars. We're going to say that's X. And we do not know what X is. X is our unknown. We're solving for X. So we're going to put X equals question mark. We don't know what it equals. And realistically speaking, this should be in red. This is what I do for my physics students. We're trying to solve for X here. Okay. But what we do know She ate 6 of them. So I'm going to say 8 because just 8 has A in it. 6 candy bars. CB is candy bars. Yeah, don't worry about that. No, I hit erase. Erase. It'll just be 6. And then 94 candy bars. That's what she's left with. We'll just make that Y. Okay. So realistically speaking here's the list of our variables with their symbols. And I just made these symbols up, and you can make these symbols up as much as you want, as long as it's identifiable. Now, what about an equation? Well, you could come up with 2 different equations here. So one equation is, you could say x is equal to 94, or sorry, not 94, a little too soon there. 94, or not 94, but x is equal to a plus y. Okay. Because we know that, 6 plus 94, she ate 6 and she started with 94. Well, we can add back the number that she ate with the number that she's left with, and we should get the number that she started with. Another way we could say, well, we know that she ate a number of them, so that'd be just x minus a is equal to y. Okay, easy enough. You could use either one. Realistically speaking, your brain probably thought of this one, but then we would have to go with this one, because we would have to more or less just use the inverse operation, because that's what you see here. That's all that's happening. So you would have to eventually add a to both sides, and that's what you would have here. Okay, so regardless what you used, those are 2 equations you used to see that x is equal to, it's not supposed to be a face, x is equal to 10, or not 10, but 100. Okay. And how do I know that? Well, x equals a, which a is 6, a plus y, which is 94. 6 plus 94 equals 100. Boom, got it. Okay, so let's look at number 2 now. So Johnny is running, I should say driving. Johnny's driving, come on, Johnny is driving at a speed with his car. He was able to drive 40 miles in 30 minutes. What speed was he traveling? Speed is equal to v, distance is equal to d, time is equal to t, and then our equation is v is equal to d over t. Now, I'll just have you know that there are a couple things in here that we haven't gone over that we do go over when we get to motion. So don't feel like you have to totally know how to do this, but you should. There is enough information here to solve for this. So what do we have? What do we know? Well, we know 2 things. More than 2 things, but we know 2 things. So we know that he drove 40 miles, and we know that he did it in 30 minutes. Okay. So we've got to now figure out his speed over this distance and over this amount of time. Okay. So let's link these up with their, so we identified, here's distance. That's our distance. Oh my goodness. Let's just say distance. And then here's our time. Okay. So, and then we're given this. So distance is equal, that's our D symbol. So D is equal to 40 miles. And then time is T, and then T is equal to 30 minutes. Now, I'll just let you know that miles per minute is technically, they are units that you can use. They aren't typically used. What is normally used is meters per second, feet per second, miles per hour, and kilometers per hour. So we're gonna use this. We're actually going to change 30 minutes to hours. So we should know though that 30 minutes is equal to 0.5 hours. Okay, we should know that. It's half an hour. Okay. So we got that. What else? What else is here? What are we solving for? What don't we have? What we're solving for is speed. It's asking what speed was he traveling? We do not have v. That's what's missing here. We got to solve for v. Okay. Well, that's fine and dandy. we've now labeled, we've identified all of our variables. Now we just have to write our equation, which is V is equal to D over T. And this one should be pretty straightforward. We just now plug in and solve. So V is equal to D over T, which is going to be 40 divided by 0.5. So 40, plot that in your calculator real quick. 40 over 0.5. You should find out that the speed was 80 miles per hour. Okay. And then you have your answer. So as you can see, there's no difference in the particular operations that are happening here. There's nothing different about the rules of algebra, algebraic of the algebraic equations here. What's different is now we're just tying it to very specific material that for the most part deals with science. So let's try another one. Okay. So Beth sets a ball with a mass of 2 kilograms at the end of a table. The amount of potential energy, PE, that the ball has is 19.6 joules. What is the height of the table? Mass is equal to M, height is equal to H, gravity is equal to G, which is also equal to 9.8. Potential energy is PE. And our equation here, hold on. I didn't. Okay, and then PE is equal to M times G times H. Another way we can write that is P is equal to MGH. So let's write down what we know and what we don't know. So what we know is that there's 2 kilograms here. There's an amount of potential energy. It's 19.6. And it looks like we're asked specifically what the height is. So I'm guessing the height, since it's asking what the height is, that's what we don't have. So let's write, so the 2 kilograms, that has to be mass. So mass is going to be equal to 2 kilograms. Okay, what else do we have? We also have the 19.6. The 19.6 is going to, that's my potential energy. Now we'll get into what joules are when we get to energy, but 19.6 joules. We also have another thing that you probably missed. It's gravity. It's G is equal to 9.8. Now I didn't give you the units because I felt the units would confuse it a bit too much without me explaining. But gravity is measured in what's called meters per second squared. So it's M divided by S to the second power. Okay, with the S with an exponent 2. And we get into that, what exactly that means when we get to energy and when we get to motion. So all you have to know is it's just meters per second squared. Okay. Okay. So we've got that. And what else do we have? Well, or what do we know that we don't have? Well, what we're solving for here, we don't know what H is. We're trying to solve for the height. Okay. What is our height? Well, let's write in our equation because we are given an equation. And our equation is PE is equal to M times G times H. Oh my goodness, what is going on? So PE is equal to M times G times H. And we're trying to solve for H. Okay. So you just got to get H by yourself. So how do you get H by yourself? Well, arguably this is a 2-step equation here. So you could say it's PE equals M. Oh my goodness, come on. Times H. And you could say that, first, you would use the inverse operation for the M and then the G. I'm going to tell you this, that we can do both at the same time. We can divide M times G at the same time to both sides. That cancels out, that cancels out, that cancels out, that cancels out, and then we're left with H is equal to PE over M times G. So notice though, did any of the rules change? No, it's exactly the same thing. Okay, algebraic rules doesn't change whether we're in science or not. Okay, it's all the same. So let's solve for that then. So let's plug that in. So H is equal to the PE over M times H, or M times G, sorry. So it's going to be 19. Goodness. So it's going to be 19.6 divided by 2 times 9.8. Plug that in, and what you should get is H is equal to 1. Now, specifically, this is going to be 1 meter. We'll get into a little bit more into how to know that, when we get to working on this. It's just more or less just canceling out all of the units, but we were, left with our height equaling to 1 meter. But again, the point of showing this and the point of going through what an equation is, to go through all the rules again of how to solve one-step equations is simply this. One-step equations are not just for math classes. They're used in science as well. And we can see that right here. You use the same things, you use the same rules, you do the same thing to find a particular solution. It's as simple as that. So it's really nothing to be worried about when we get to these kinds of math equations, whether it's in science class or it's in math class. Again, they are using the same question or the same rules. Okay. It's just now the trick of remembering all those rules and remembering how to do everything. So to end this with these two last slides, so the greatest thing you can do is go back and double check your answer. Plug in your answer into the original equation and see if the variable you just solved for is the actual solution. If you don't get the answer you're looking for, you need to go back and figure out what's wrong. Okay. So for instance, in the previous question with Beth putting putting that ball at the end of the table, multiply 2 times 1 times 9.8. See what you get. Seriously, see what you get. You should get this number right here. Okay. And that would tell you that the solution is correct and that is the true solution. Okay. Go back, double check your answer. Always, always, always. It's I can't stress how much of a great skill that is. So once you have the answer, don't forget to include your units. That's something I'm going to be getting on you guys a whole lot about in this class and future classes as well. Numbers by themselves don't mean anything. You have to include your units. I don't know if that 5, if you put down 5, what does that 5 mean? Does that mean 5 miles? Does it mean 5 meters? Does it mean 5 seconds? Does it mean 5 kilograms per meters per second squared? Does it stand for 5 joules? Does it stand for 5? You understand what I'm saying here. You have to include units. We get into that further when we get to the actual material, but don't forget, go back, check your answers, include units. And that's all I have for you guys. So if you have any further questions, make sure you ask me, but that's the lecture for today. Hope you guys have a good one. I'll see you in the next one.